In this video, we will be talking about measures of variation. Our learning objectives will be to find the range of a dataset, find the variance and standard deviation of a dataset, and to interpret the standard deviation. In the previous video, we talked about measures of average. And now that we've considered measures of average, let's consider the fact that there's more to the story told by a dataset than just the average. In this section, we will study measures of variation, which will help to describe how the data within a set vary. The three most commonly used measures of variation are range, variance, and standard deviation. Let's take each of these one by one, and starting with the range. The range is the simplest of the three measures of variation that we will study. The range of a dataset is the difference between the highest and lowest values in the set. So the range is simply the highest value minus the lowest value. That's all it is. Let's look at an example where we will find the range for a couple of data sets. The first list below is the weights of 4 large dogs, and the second is the weights of a mix of small, medium, and large dogs. Find the mean, median, and range for each list, and then describe any observations that you can make based on the results. So let's start with list 1. Okay, so let's say list 1. Okay, so for the mean, our symbol for the mean is X bar. We add up the numbers and divide by the number of numbers. So this would be 70 plus 73 plus 58 plus 60 divided by 4. And if you do this calculation, you get 65.25. Okay, that's the mean. To find the median, we need to rearrange the numbers in order first. So to do that, I would get 58, 60, 70, and 73. The median is the number in the middle, and since there are 4 values in the data set, I will take the 2 middle values and I will add them up and divide by 2 to find the median. So the median is equal to 60 plus 70 divided by 2, and that equals 65, sorry. And then the range is just the largest value minus the smallest value. So that would be 125 minus 30. Sorry. And that equals 95. And these all have units of pounds. So let's just go ahead and put units on these. Okay. So that's list 1. List 2. Okay. For the mean, this one I've got more numbers, so you add them up. 30 plus 85 plus 40 plus 125 plus 42 plus 76 plus 60 plus 55. And divide this by the number of numbers, which is 8 in this case. And that works out to be 64 pounds. Okay. For the median, we arrange the numbers in order to start with, which gives us 30, 40, 42, 55, 60, 75, 85, and 125. Okay. Once again, there are an even number of numbers, in this case 8 numbers, so there are 2 middle numbers, 55 and 60. So the median is found by adding those 2 numbers up and dividing by 2, which gives me 57.5. Okay. And then the range, I just realized I made a mistake. I apologize. But the range for the first set of numbers is actually 73 minus 58, okay, which equals 15 pounds. And then the range for the second list is what I had previously. So 125 minus 30 equals 95 pounds. So there we go. Sorry about that. So what we observe after doing all of this is we see that the means and the medians are similar for both data sets, but the ranges are very different. So this tells us that using an average by itself is really not enough to characterize a data set. If we were just relying on an average, we might come to the conclusion that these two data sets are pretty similar, because if you compare the mean, right, the mean from the first one is 65.25, 64 on the second one, right, those are fairly similar. The medians are a little different, 65 versus 57.5. But what really is a huge difference is the difference between the range, right? So for the first list, we see a range of 15, the second list, a range of 95. Okay, that tells us that there's quite a bit more variation in this second list here. A lot more variation in size among the dogs in the second list. If you look at the 4 numbers in list 1, we can kind of see that, right? We see that they don't, there's not a whole lot of variation there, right? From 58 pounds at the low end to 73 pounds at the high end. But over here, we see it anywhere from 30 to 125 pounds, right? That's a huge amount of variation in the data values there. Now, so it's helpful to have some way of characterizing the variation of a data set, but the range is a pretty limited measure of variation because it ignores all the data except the highest and lowest values. If most of the values are similar, but there's just one unusually high value, the range will make it look like there's a lot more variation than there actually is. For this reason, we will next define variance and standard deviation, which are much more reliable measures of variation because they incorporate all the values in the dataset, not just the smallest and largest values. Variance and standard deviation are a little tricky to compute. In the box below, we will explain how to find them. And then later in the section, we will discuss their significance. So in this video, I'm going to go through an example where we calculate the variance and standard deviation by hand. However, it's also worth mentioning that a lot of scientific and graphing calculators are equipped with built-in functions to kind of do this calculation for you. And there is a separate video in the learning module that goes over how to use kind of a typical calculator, I think a TI-30, which is a fairly common one, to find standard deviation. So I strongly encourage you to watch that video. And if you learn how to use the functionality on your own calculator, you're welcome to use that for homework, exams, etc. Look for that other video to see how to use a calculator to do that. In this video, we'll be focusing on the hand calculation. So let's move on to example 2 here. Find the variance and standard deviation for the weights of the 8 dogs in the second list from the previous example. The weights are listed again for reference. We want to follow the procedure up here, this 6-step procedure. Okay. So step 1, find the mean, right? We actually already did that in the previous example, right? We found the mean to be 64 pounds. There it is right there. So we don't need to redo that calculation since we've already done it. X bar equals 64. Okay. Step 2, subtract the mean from each data value in the data set. So I'm going to take each of the 8 values in the data set, and I'm going to subtract 64 from each value. If I do each one, I've got 30 minus 64, which equals negative 34. And then I've got 85 minus 64, which equals 21. 40 minus 64. Okay. This equals negative 24. 125 minus 64 equals 61. Okay. 42 minus 64 equals negative 22. 75 minus 64 equals 11. 60 minus 64 equals negative 4. And then finally, 55 minus 64 equals negative 9. Okay, that's step 2. Step 3, square the differences. So I want to take each of these numbers that I just computed, these differences, and I want to square them all. So taking each one in turn, the first one is negative 34. If I square it, I get 1,156. Okay. The second one is 21 squared, which equals 441. And then negative 24 squared, which equals 576. And then 61 squared, which equals 3,721. Then I have negative 22 squared, which equals 484. And 11 squared, which equals 121. And negative 4 squared, which equals 16. And then negative 9 squared, which equals 81. Okay? So that's step 3 that we just did. Step 4 is to find the sum of the squares. So now I'm going to take all the squares that I just calculated and add them together. So that's going to be 1,156 plus 441 plus 576 plus 3,721 plus 484 plus 121 plus 16 plus 81. Okay, these add up to 6,596. Okay, so that is the sum of the squares. That was step 4 that we just did. Step 5, divide the sum by n minus 1 to get the variance, where n is the number of data values. So there are 8 data values. So 8 minus 1 is 7. So I will take this sum, the sum of the squares, and divide that by 7. And that's going to be my variance. So my variance is equal to 6,596 divided by 7. And that works out to be approximately 942.3. Okay. And then the other measure of variation is called the standard deviation, and that is found by taking the square root of the variance. Okay, so the standard deviation this is equal to the square root of 942.3, and that works out to be about 30.7. And this number has units. The original data had units of pounds. Standard deviation has the same units as the original data. So that's the procedure. As you can see, it's a little bit of a tedious process. To organize the steps, you might actually find it helpful to make a table with 3 columns. The first column, we just list the original data. The second column, we list the difference between each data value and the mean. And then in the third column, we just list the squares, right? So original data, subtract the mean from each original data value, square each of the values in the second column here. And then you just add the entries in the last column and divide by n-1 to get the variance. To understand the significance of standard deviation, let's take a deeper dive at the process, one step at a time. Step 1, compute the mean. Variation is a measure of how far the data varies from the mean. So it makes sense to begin here by computing the mean. Step 2, subtract the mean from each data value. In this step, we are literally calculating how far away from the mean each data value is. The problem is that since some are greater than the mean and some are less, their sum will always add up to 0. This is why, so essentially what we're trying to do in this process is calculate the average deviation away from the mean, right? So that's why in step 2, we're finding the actual deviations away from the mean. But once I find these deviations, I can't just average them. I can't just add them up and then, say, divide by the number of numbers by calculating an average, because the deviations will add up to 0. Some are positive, some are negative. They will always exactly balance each other out. So it doesn't help much to just add them up, because the sum will always be 0. So that's why we do step 3 here, where we square the differences. This solves the problem of those differences adding to 0. When we square them, they're all positive. Step 4, add the squares. In the next 2 steps, we're getting an approximate average of the squares of the individual variations from the mean. Because remember, when you calculate a mean, you add up numbers and you divide by the number of numbers. Step 4, we're adding up the numbers. The numbers we're adding are the squared deviations away from the mean, right? That's what we're adding. Step 5, divide the sum by n-1. This one's a little counterintuitive, because it seems like, based off of what we know about calculating a mean, dividing by the number of values here would be a good idea instead of the number of values minus 1. However, it turns out that when we're using a sample from a larger population to compute the mean and variance, which is what we're doing in these cases, dividing by n-1 actually makes the sample variance more likely to be a true reflection of the population variance. So it's basically a bit of a correction factor to make your sample variance look more like a population variance. In any case, at this point, we have an approximate average of the squares of the individual variations from the mean. Step 6, take the square root of the sum. This undoes the square that we did in step 3, and it will return the units of our answer to the units of the original data, which gives us a good measure of how far the typical data value varies from the mean. So sometimes variance is considered kind of its own measure of variation, but standard deviation is actually really a better one because by taking that square root at the end, it normalizes the units, right? So we end up with a measure of variation that has the same units as the original data, which makes it more useful. Okay, so now we will formally define these two key measures of variation in formula form. A lowercase s is typically used to represent standard deviation, which means s squared is used for variance, right? Highlighting that relationship between them. So here's our formal definition. The sample variance for a data set is an approximate average of the square of the distance between each value and the mean. If x represents individual values, x bar is the mean, and n is the number of values. So then s squared, the variance, is equal to, remember this is the Greek letter sigma, and it means sum or add. So the sum, and then here it says x minus x bar squared, right? So it's literally saying take the sum of the squared deviations away from the mean and divide by n minus 1. The number of data values minus 1. The sample standard deviation, s, is the square root of the sample variance. It provides an approximate average of the distances between data values and the mean. Okay, now that we know how to calculate a variance and a standard deviation, let's talk a little bit about how to interpret it. Since standard deviation measures how far typical values are from the mean, its size tells us how spread out the data are. So we'll examine this idea in examples 3 and 4. So example 3, these are mostly just kind of scenarios that we need to think through here. The mean and standard deviation for heights of all adult males in the United States are 69.3 inches and 2.8 inches, respectively. The mean and standard deviation for the 2021-2022 Cleveland Cavaliers, a professional basketball team, on the other hand, were 77.4 inches and 3.74 inches. What can we conclude from comparing these statistics? Well, there are really kind of two main things we can learn from these comparisons. First, the obvious one here is that the members of a professional basketball team tend to be a lot taller than average people. And if you've ever watched a basketball game, this comes as no surprise, right? It's just basketball players tend to be, on average, taller than most other people. And second, the heights are spread out a bit more than the population in general, which we can see by the difference in the standard deviations, right? For the basketball team, the standard deviation was 3.75 inches. For adult males in general, 2.8 inches, right? This could be due to the small sample size, right? We're talking about a sample of 18 players for the basketball team versus all adult males, right? So obviously these numbers are based off of a much larger data set, right? But it might also be because there are some basketball players that are good players because of speed and athleticism, even though they're not that tall, while others are successful to some extent because of their extreme height. In order to draw more reliable conclusions, we'd probably need to look at a much larger sample of pro basketball players instead of relying on just a single team, right? But those are just, what's pretty obvious is that the average height is much higher, right? The reason for the difference in the standard deviations is a little bit less obvious. We can make some educated guesses, but to draw more firm conclusions, you'd need a larger sample size, a larger data set. Okay. Let's take a look at this next example. A professor has 2 sections of Math 115 this semester. The 8:30 a.m. class has a mean score of 74% with a standard deviation of 3.6%. The 2 p.m. class also has a mean score of 74%, but a larger standard deviation of 9.2%. What can we conclude about the students' averages in these 2 sections? Well, basically what we can see, what's obvious, is that the morning class has a small standard deviation, and the afternoon class has a large one. So even though they have the same mean, the classes are quite different. In the morning class, most of the students probably have scores relatively close to the mean, right? So every individual student's score would not vary that much from the 74% average. In the afternoon class, the scores vary more widely, with a lot of high scores and a lot of low scores that average out to a mean of 74%. So that's what we can say about those 2 data sets. Okay, that's it for this video. I hope you found that helpful, and thank you for watching.